So what we are going to do today? Heat transfer. Okay. Now heat transfer, when we talk about in our syllabus, there are two modes of heat transfer. Okay. And those two modes of heat transfer are conduction and radiation. Okay. Two modes are conduction and radiation. Heat transfer means what? And why heat transfers from one body to another body, or maybe within the same body. Okay. So we already studied that heat flows from higher temperature to lower temperature. Higher temperature to lower temperature. This we have studied already. So whenever temperature difference is there, heat will flow. Okay. So its example is conduction. In conduction, heat flows within the same body because of change in temperature. What does that mean? If suppose we have a conductor. Now conductor we already know. Okay, in electricity also we talk about conductor, right? Conductor is one through which current can flow because there is availability of free electrons. In electricity we say that. Here also conductor is one through which heat can flow, right? Suppose this is a conductor here. Here its temperature is TA, here its temperature is TB. So if temperature is at A is greater than TB, then what will happen? It will flow from higher temperature to lower temperature. Okay, it will flow from higher temperature to low temperature. Now this heat, if I am going to say flow of heat per unit time, okay, and if heat I am going to represent with Q, okay, now I don't write over here, okay, because we are going to say this is H, okay. So if heat or energy we represent with Q, then rate of heat flow, rate of heat flow or energy flow will represent with H, and what is that? That is delta Q by T, or you can say dQ by dt. Rate of heat flow, kind of energy per unit time, you can say power also. Okay. So rate of heat flow we are saying is H, that is equal to dQ by dt, or we can call it as heat current also. This is heat current. What is heat current? H. Okay. So heat current is H, this H. So it's very similar to electric current. How? Because in electric current what we say? Electric current we used to say according to Ohm's law. We say I equal to delta V by R, and R is resistance. Same way here also. Okay. Here we say H is equal to delta T by R. And what is this? R is thermal resistance. H equal to delta T by R. So this depends on temperature difference. That's what we say. Heat flows from higher temperature to lower temperature. Here current used to flow from higher potential to lower potential. Here it is moving from higher temperature to lower temperature. So H is equal to delta T by resistance. So delta T is what here? TA minus TB. Now what is resistance? Now if you remember, in electric current, the resistance, if suppose we have a conductor like this, okay, conductor with length L, okay, its length we are taking as L, and conductivity we take as sigma. This is V1, this is V2, okay. So its resistance we used to write as what? Resistance we used to say is rho L by A, and rho was what? Resistivity, and resistivity is equal to what? 1 by conductivity. So resistance used to be L by sigma A. Okay, exactly same thing here. Thermal resistance is L by thermal conductivity into A. If suppose its thermal conductivity is K and area here is A, okay, this area is A, then thermal resistance is going to be L by Ka. Exactly same way. Length of the rod, thermal conductivity, area. Okay. So this is thermal conductivity. Thermal conductivity like this. This was the conductivity of this wire. Same way here for this wire or this rod. This is thermal conductivity. That is property of the medium. That is property of the medium. Resistivity, conductivity as we studied over there. Same way these are for here also. Okay, so what is the formula? What is H? H final formula is Ta minus Tb by resistance means L by Ka. So it is Ka delta T by L. Okay. Now the question comes out, what is the unit or dimension, unit and dimension of K? Okay. So what we can do? Let's see. What is the unit and dimension of this? Okay. So now here H is what? Rate of flow of heat. That means joule per second. Joule per second means what? Okay. So we can write over here what? Temperature difference means Kelvin. Okay. So I am writing Kelvin because K is already there. So I should not be writing this also K. Okay. So K, here is K. Meter square is area and length is meter. So meter and meter gets cancelled. So what we are getting? Watt per meter per Kelvin is unit of K. This is unit of thermal conductivity. Dimensions. Dimensions also we can find. What is watt here? What is energy per unit time? So dimensions also we will see. Dimensions we will make where here we will see. The dimensions of K. Okay. So first we are going to write dimensions of power. Power is energy per unit time. Energy is M L square T minus 2 for energy per unit time. So time also will go up. So ml square T to the power minus 3. That's power. Okay, then by meter. So by meter means L. And then temperature. So temperature I am writing as theta. Okay, Kelvin. So what we are getting? M L to the power 1, T to the power minus 3, theta to the power minus 1, M to the power 1. So this is dimension of thermal conductivity. Okay, right? Let's see the question. Now there is only one formula. Only one formula is there in conduction. What is that formula? H equal to delta T by R. And R value L by K. There is no other formula in thermal conductivity. Whenever there is temperature difference, heat will transfer from one end to the other end, or heat will conduct from one point to the other point. Okay. Okay, let's see questions then. So questions is, this rod is given to us, and in this rod, this temperature is 100 given, this temperature is 60 given, this is 2L. Okay, total length of the rod is 3L, and we can take its area as A. We have to find temperature at P. Okay, this rod, this end is maintained at 100, this end is maintained at 660 degrees, length is 3L, area is A. In between the rod there is one point P. We have to find temperature at P. So what we know from our knowledge of current electricity. So what I can do is, if suppose in the same way we have to make, so same rod, suppose like this I am making, this is the rod, okay, and this we are connecting with a battery, okay. So first rod should be made slightly in a different way, right? Okay, we'll make it slightly thicker. This is our rod, okay. Then we are connecting it with a battery. The battery is like this. Okay, the battery is what? 40 degrees centigrade. What is that? Delta T. Check, delta T is 40 only. Okay, now what is he asking? He's asking temperature somewhere here. What is temperature here? Okay, and this is given to you as 2L. and this is given to you as L. That's all? Yes. Okay. So now what we know, this in this entire wire, same current will go. Single wire. So current is I. So here I'll say current is H. H only is going throughout. Okay. Here, what is the difference? Now, remember that in battery, we used to write potential difference. So here also what I have written temperature difference directly. Correct? No problem? Okay. So H is what? Delta T by R. Correct? So if its resistance I can know, then I know everything. Correct? So if H we know, R we know, and temperature at this end we know. Temperature at this end we can find very easily. Correct? Right? So how to find H first? So H I am finding. What is the temperature difference? Temperature difference is 40. And what is its resistance? Resistance is L by Ka. L is 3L by Ka. So H value I know, that is 40 by 3L, and this is Ka. Perfect. Now what you want? Now I want temperature at this end. So now what I'll do? I'll just write this is 100 because that's required now. Okay. So now what? Same H, no, here also. Yes, here also same H. Okay. So see now, I'm writing same thing now. Okay. So H equal to, now what I'll do? This end is A and this end is B. Let's assume. Okay. So H equal to Ta minus Tb. Temperature difference between the two by 2L into Ka. Okay, H value is this, that is 40 Ka by 3L equal to Ta is 100, Tb we are finding, Ka by 2L. Okay, so Ka cancelled, L cancelled. This is 40 by 3 into 2, this 2 equal to 100 minus Tb. So Tb equal to 100 minus 80 by 3. It will be 220 by 3. Okay, temperature at T will be 220 by 3 degrees centigrade. This I just tried to make it in terms of current electricity. If you don't want directly with this, you want to write this is 100, this is 60, then is also fine. We can still find delta T as 40 only. Just to make it similar, I made it like this. Your wish. Okay. So now temperature is 220 by 3. This way we have to find. So just do it exactly same way as we do current electricity. It will be very easy for you. Okay. Sorry. See another one. This is the rod. This temperature is 50. This is 20. This is T, and T you have to find. Total length of the rod 4L, whereas this is 3L, and area you can say is A. Similar question. In the previous question, this and this was given, this was asked. Now here this and this are given, this is asked. Okay. So now what to do? Same formula. H equal to delta T by R. Same heat will flow from here to here throughout. Yes. Yes. Same heat will flow. Okay. What we have to find? Let's write that first. This is 50. Here temperature is T. So delta T is this by 4L into Ka. Okay. Thermal conductivity assume as K. Okay. In this one we have to find T. Okay, fine. This H is here also. So one more time you write H equal to temperature difference is what? 50 minus 20. So that is 30. Length is how much? 3L by Ka. Okay. So H value is what? 10 Ka by L. This value we are going to put here. because same heat is going from here to here, same heat is going throughout. Okay, so put it 10 Ka by L equal to 50 minus T into Ka by 4L. Ka cancelled, L cancelled. 10 into 4, 40. So 40 equal to 50 minus T. So T equal to 10. So here temperature will be 10. That is it. Over. Okay. So this way we can say that throughout the wire same current is passing. Okay, you can call this a series connection also if you want. This is one section of wire, this is another section of wire. So in series connection of the thermal resistors, same current passes. Okay. Okay, anyhow this is combination of rod has come. Now what is the combination here? In this combination you can see there are two rods, right? There are two rods here, and if I can show you clearly, it's like this. There are two rods. Okay, one is this one, another one is this one. Its area is A, its area is 2A, TA, TB. This is 300 Kelvin, this is 200 Kelvin. And what is the question asking? How much is heat through this? Okay, how much is heat through the first one? In fact, Q1 they are asking. The Q1 is placed at wrong place. So this I will just remove. Okay, it's not Q1. Right. Okay, this is not Q1. This is Q, and this is here Q1. Okay, so through upper one, the heat flow is Q, below one heat is Q1. So what is Q1 he is asking? Simple question here. Here also temperature is 300, here is temperature 200. So first we will write what is Q value. After that only we are going to talk about Q1. Thermal conductivity is same. Okay, this is also K, this is also K. They are made from the same metal or same material. Okay. So Q first I am writing. What is Q? We know that formula says delta T by R, that is delta T by L into Ka. So see what we can write. Delta T means 300 minus 200, that is 100 Kelvin, into K into A by L. This is Q value. Okay. Temperature difference 100, K, A by L. Now we have to find Q1. Q1 what it is? Q1 we are writing again 100. This is K. Area is 2A by L. So if this is Q and this is 2Q, what else? That's it. It's over. So from here Q is going, from here 2Q is going. Okay. Okay, see again, one more. This is one rod, rod number 1. This temperature 100, this temperature 0. This is thermal conductivity K, area A, length L. It says that this rod melts 6 gram ice in 2 seconds. How heat will be flowing? From here to here. This is at 0, definitely ice is here. Okay, so heat is coming and melting the ice. How much ice is melted? 6 gram in 2 seconds. Another rod is there. This is 100 degrees centigrade, this is 0. Thermal conductivity 2K, area A. He says how much time this rod will take to melt 3 gram of ice. So ice is here again. Only 3 gram of ice we have to melt. How much time it will take? This rod will take. That's the question. Okay, so let's start. So first for this rod we are writing how much heat is getting transferred first of all. H is how much? So H is 100 minus 0 by L to Ka. That is 100 Ka by L. This is heat transfer per second. Okay, this is power. Okay, it's in watt. So what it is required now, how much heat is required? He wants to melt 6 gram of ice in 2 seconds. So 6 gram of ice you have to melt. That means what does he require? Latent heat. I mean to L. Okay. Now L means here, if you remember, you can put calories. Okay. So right then, 6 gram of ice is melt. Okay. So amount of heat required is 6 into how many calories? 80 calories per gram. So 480 calories it required. Okay, correct? In 2 seconds. So what you will do? This is per second. Okay, and this much calories you require. So we will say that H into how many seconds? 2 seconds. This is heat flow per unit time. Okay, these many calories per second. So H into 2 equal to 480. Okay, so H is how much? 240 calorie per second. Okay, fine. Okay. Right, come here. Now what is here? How much is heat in this case? Say H1, and H1 is how much? Temperature difference 100. This is by L, and this is 2 Ka. Now, by seeing this one itself, this is 100 Ka by L, this is 200 Ka by L. Already we know that it's 2H, right? This is equal to 2H. Now 3 gram of ice here to melt. Okay, so heat required is how much? ml, you know that is 3 into 80 calories per gram. Correct? How much heat is coming? 2H. And how much time it's going to take? Let's say T. T is only is asking. 2H means what? 2 into 240 into T equal to 240. So at 240 gets cancelled. T is just half a second. In half a second, it will melt 3 gram of ice. Okay, simple question. What we did, just this formula. And where it is used? In melting the ice. Right? Similar question, one more we'll see. Now here it is series connection here, and this is parallel connection. Okay. In series connection, what do you know? Throughout same current will pass. But in this case, different current will pass. We'll find that how much is current, right? See. Okay. So let's start here. So if it's series connection, shall we use like series connection only? Okay. There are two rods. This is R1 and this is R2. So series connection means resistance will be R1 plus R2. Okay. So R1 is what? L by 2K into A plus L by Ka. Okay. So what we are getting here? This is L by K. If you take common, it is 1 by 2 plus 1. That is 3 by 2 then. 3 by 2 L by K. That is the resistance. Okay. Here temperature 100, here temperature is 0. So what we want? I value, that is H value, sorry, not I value. H value we want. So H value is delta T by R. Delta T 100 by 3L and here is 2 Ka. Okay. So 200 Ka by 3L. That is H value. Okay. What is this? This combination will 6 gram of ice in 2 seconds. Okay, fine. So H, similar value is this. I am directly using H into 2 seconds. Okay. Rate of heat flow per unit time into 2 seconds equal to 6 gram of ice into 80 calorie per gram. Okay, H value is what? 200 Ka by 3L by 3L into 2 equal to 480. Okay, then this is 240 here, 240 into 3L. So what are we trying to calculate? Actually, Ka by L value. Okay, Ka by L is what? 240 into 3 by 200. Okay, keep it with us. Now, this is here, parallel combination. Now, parallel combination, what happens? That also we know. Their resistance is 1 by R equal to 1 by R1 plus 1 by R2. Okay, so let's do 1 by R equal to 1 by R1 plus 1 by R2. So 1 by R is, R1 is what? Anyone we can take R1, suppose this one. So R1 is equal to L by 2Ka. Okay, R1 is L by 2Ka and R2 L by Ka. So 1 by R1 means 2Ka by L and 1 by R2 means Ka by L. So 1 by R is equal to 3Ka by L. So R is equal to what? L by 3Ka. Okay, now we converted them in single resistor of this resistance. Okay. So current is what? H1. H1 equal to temperature difference is same 100 minus 0. So 100 by resistance. What is resistance? This is L and this is 3Ka. Okay. Right. So now what you will do? We have to melt how much ice? Same ice. Okay. So we will write what? H1 into T equal to 6 gram of ice into 80 calorie per gram. Right, 480. H1 is what? 300 into Ka by L into T equal to 480. Now Ka by L value you already have. 720 by 200. Let's keep it. This is 300 into 720 by 200 into T equal to 480. Okay. So what it is here? This two zeros and this 2 zeros is cancelled. Then what else we can do? T equal to, let's do it up above here. We have little place. So T equal to 480 into 2 by 720 into 3. 720 into 3. Okay. So this is cancelled first and this is 16. Then this is 8 2 just 16. This is 8 9 ja. That's all. So 4 by 9. 4 by 9 seconds it will take. Okay, so this one more heat is transferring as compared to this one because here resistance is more, here resistance is less obviously. See resistance how much here? 3 by 2 L by Ka, whereas here is 1/3 L by 3 Ka, not 1/3, even less. Okay, this is 1.5 and this is 0.3, right? So 1/5 in fact. So that's how the heat in parallel connection is more as compared to series. Okay, exactly like current electricity, you have to do it. It will be easy. If you think in different way, no, it can create confusion in your mind. So you don't do like that. Okay. All right. Thermal conductivity of combination. Okay, this question commonly asked. So if we are going to take, suppose two rods we are taking like this. Okay. Two are like this here. Okay, we have shown both are different, and its thermal conductivity says K1, its thermal conductivity is K2. Area you may take same, or you can take different also, your wish. Okay, A and A. Here temperature T1 and T2. Okay, but that may not be required. Length you can take L or L1 or anything. Maybe L only you take. Easy for you. This is L and this is also L. So what we know, if they are series combination, then R is equal to R1 plus R2. Okay, what is R1? R1 is L by K1A. What is R2? L by K2A. And net resistance, what we will write? This is 1. If net resistance we are talking, this will become 1. So what is this length? 2L by, what are we finding? Thermal conductivity of combination. So K effective, okay, by area. Length is 2L, K effective by area. Okay. Now what you can cancel in this one? L and A you can see here also, here also, here also. Okay. So 2 by K effective is equal to 1 by K1 plus 1 by K2. Okay. Take their LCM. K1, K2 here. This is K2 plus K1. Okay. So K effective is K1, K2 into 2, K effective 2 K1, K2 by K1 plus K2. Okay, if L1 and L2 are given, no problem. Here will be L1, here will be L2, and here will be writing in place of 2L, it will become L1 plus L2. That only is the difference. Area cannot be different in this case. Area will be different in parallel combination. Okay, so here area will be same because you want same current to pass, right? So resistances have same area. Now parallel also we'll see. So here is one. Okay, and take one more. And in this one we want to have slightly larger area of this one, so we can make. Okay, so area of one is different than the area of the other one. Okay, so these are two resistors. This is K1, this is K2, and its area, let's say, is A, its area is 2A. Okay, length you can say is L. Here length is same, has to be. Okay, length is same. Then what else? That's it. So it's in this one, resistance is what? Resistance we say is R1 R2 by R1 plus R2, or you can write 1 by R equal to 1 by R1 plus 1 by R2. That's your wish. Okay, what is R1? So R1 is L by K1A and R2 is L by K2 into 2A. We have written it like we have made area same also we can do. So R is equal to what? Or 1 by R, shall we write 1 by R only? 1 by R equal to 1 by R1 plus 1 by R2. Let's keep the value of R1 and R2. R1 is L by K, so this will be K1A by L plus 2 K2A by L. So 1 by R we can write what? K effective. Now how much is area? 2A plus A, that is 3A by L. Okay, so you can see L gets cancelled. L and area A and A gets cancelled. So what we have now? K effective is K1 plus 2K2 by 3. If you are having different area, this is A1 you are writing and this is A2 you are writing, no issue. Here is A1, here is A2. and here will be A1 plus A2. Okay. So we can get thermal conductivity in like this, whether series connection or parallel connection. Okay. Many questions you will find like this when you see any of the book that through which you are practicing, and even in NEET also. Okay. Now we are going to see how to find temperature of junction. Junction, then you go back again, current, electricity. There was junction law of Kirchhoff. What it says, at any junction, the current which is coming towards it will be equal to the current going out of it, right? So here this junction is given, its temperature we have to find. So current coming towards it will be equal to current outgoing from it. So from where current is coming, this is 300 Kelvin, this is 200 Kelvin, that is 50 Kelvin. So we are saying that okay, from here H1 current is coming, from here H2 current is, from here also H2 is coming, and here H1 plus H2 is going. This is what we can say. Correct. What is H1? The H1 is, this is T, okay. So temperature difference is 300 minus T by resistance LKA. So L into Ka. This is H1. Okay, what is H2? H2 is 200 minus T, and here also Ka by L. Okay, there H1 plus H2 is what? H1 plus H2 is equal to T minus 50. Okay, then 3K is there. Okay, so 3K into A by L. Okay, all three currents I have written by given data. Now what I have to do? H1 plus H2, I have to keep this over here. Okay, nothing else. Let's keep it this. Okay, so 300 minus T by L into K. Let's put it here. 300 minus T into Ka by L plus 200 minus T into Ka by L equal to T minus 50 into 3Ka by L. T minus 50 into 3Ka by L. What we can cancel? You can see Ka by L, this, and this is cancelled. Now let's solve it. 300 minus T plus 200 minus T equal to 3T minus 150. Okay, so 300 plus 200, 500, and this 150 also will come, 650. Minus T, that is minus 2T will go that side, so it will become 5T. So T equal to 130 Kelvin. That's all. Temperature of the junction 130 Kelvin. So like this, any combinations question we can do. Remember Kirchhoff's law. Okay, incoming current equal to outgoing current. Okay, fine. See this also. What it says that there is this, you can say, one metal slab is there. Okay, like glass slab we see in optics. This is metal slab. Here steam is there at 100 degrees centigrade. Here ice is there at 0 degrees centigrade. So what we want? Area is given. 4.8 kg ice melts in 1 hour. Find K. 4.8 kg ice melts in 1 hour, and we have to find its thermal conductivity. Latent heat of fusion of ice given as 3.36 into 10 to the power 5 joule per kg. Okay, similar type of question we did already, right? 6 gram of ice was melting in 2 seconds something. Similar here, 4.8 kg ice melts in 1 hour. So how much is heat required? Okay, heat required. ml. Okay, so 4.8 kg into 3.36 into 10 to the power 5. This much is heat required. How much? Joule. Okay, now what is happening? How much heat is getting transferred from here? Let's say H. H is what? Delta T. Delta T is 100. K. A is 0.36 by length. Length is 0.1 meter. Okay, so this is transferring per second. He says in 1 hour, this much amount of heat is transferred. So 1 hour means H into 1 hour equal to this 4.8 into 3.36 into 10 to the power 5. Right? Okay. H is what this. So let's do that. Okay. So put it over here, 100 into 0.36. 100 into 0.36 means 36. 36 by 0.1, 360. Okay. So 360 into 1 hour. 1 hour means 60 minutes and each minute is having 60 seconds. So 360 into 60 into 60 equal to this. Okay. But what I left is K I left. Yeah. So K is here equal to 4.8 into 3.36 into 10 to the power 5. Okay, so this is 1 0, this is another one, then another one. So here 3 zeros has gone. So this is now. So this is 48 into 33.6, where here is 36 into 36. Okay, so this is 4, this is 3. So K value is 33.6 into 4 by 36 into 3. Okay, more we can calculate. This is 9. Okay, then this is 3, 1.2, 11.2 by 9. Okay, 1 point something will come. So this is how questions will be asked from you on conduction. Okay, let's see what next is. Okay, one more question is there. This is the small rod. Here is temperature TA, here is TB, K1 is thermal conductivity, A1 area, length is L, and through this one, Q1 is the heat current. Here, same TATB, but the rod is different, thermal conductivity is different, area different. So, heat current is Q2. So, he says if Q1 is equal to 4Q2, then what is the condition? Okay, fine. So, we will make Q1 equal to 4Q2. So, what is Q1 here? Q1 is TA minus TB by resistance. Resistance means L, and here is K1A1. Okay, Q2 is what then? Q2 is again TA minus TB by L to K2A2. Now, what we have to do? Q1 equal to 4Q2. Okay, Q1 equal to 4Q2. So, TA minus TB into K1A1 by L equal to 4 TA minus TB into K2A2 by L. So, TA minus TB is cancelled first. L is cancelled. That's it. K1A1 equal to 4 times K2A2. That is the condition. Okay, that is the condition. Alright, what next? Two ends of rod are maintained at 100 and 110. Then heat current is 4 joule per second. If ends are at 200 and 210, then what is Q? Okay. So this is the rod. In two cases, both we made. In first case, this is 110 degrees centigrade and this is 100 degrees centigrade. Okay, let's assume this is K, this is A, and this length is L. Same way here is 210. and this is 200. Same rod, so K, A and L. Okay, here heat flow is 4 joule per second. So I am writing 4 equal to temperature difference 10 by L into Ka. This is given. Here this is Q. Again temperature difference 10. This is L. This is Ka. Okay. So what do you say? This and this look same. So same 4. Same 4. This Q is also 4. So it means it depends only on temperature difference, not what the temperature of individual end is. Here is 110 and 100, here is 210 and 200. In both the cases, heat flow is same. Okay. Okay. So this is it as far as conduction is concerned. Now then, we are moving on radiation. Right. So radiation is also a type of heat transfer, but this heat transfer is slightly different than other heat transfers. Why? Because this radiation means how much emission you are doing. Okay, how much you are emitting. Okay, this is emission actually. So this radiation doesn't depend on temperature difference. It only depends on your temperature. This depends on your own absolute temperature. It doesn't depend on temperature difference. How much is the other body having? It has nothing to do with that. It is only proportional to your own temperature. Okay. Radiation depends on absolute temperature of the object. Absolute temperature of object. Okay, it does not depend on temperature difference. It does not depend on temperature difference. So at every temperature is going to radiate. Answer is yes. Okay, object radiates energy at every temperature. Radiates energy at every temperature except absolute zero. Okay, except absolute zero, that is right. This is radiation. Okay, then what we have? Okay, we have direct question. Right then, so what is power emitted then? Okay, so power emitted is given to us by Stephen's law. Now what is Stephen's law? Stephen's law says that power emitted by a body is directly proportional to fourth power of its absolute temperature. Okay, fourth power of its absolute temperature. Then it is also proportional to surface area of the object. Okay, and it's also proportional to emissivity. If it's not a black body, if it's a black body, emissivity is 1. Okay, but if it is not a black body, then it depends on emissivity also. So this power, if we combine, then formula comes out to be E A sigma T to the power 4. Okay, T to the power 4 this only, and this A is surface area. E is emissivity and sigma is Stephen's constant. E is emissivity and emissivity's value is always less than 1. Okay, emissivity is always less than 1 because it's not for a black body. Black body E is 1. Okay, so for black body we'll be writing this formula as A sigma T to the power 4. Okay. That also I'll write over here. E for black body is 1. Okay. So E A sigma T to the power 4. Sigma is Stephen's constant. Sigma is Stephen's constant. And it has got a value 5.67 into 10 to the power minus 8. Okay. 5.67 into 10 to the power minus 8 joule. No, watt per meter square per Kelvin. Watt per meter square per Kelvin. Okay. That is sigma value. E is what? What is E actually? E is emissivity. Emissivity is actually ratio. Okay. Ratio of emissive power of body by emissive power of black body. So that's why it comes out to be less than 1. Okay. Right. Let's move ahead and see what question is now. Based on this formula only. This is the main formula in this chapter. Okay, this topic. Power radiated is EA sigma T to the power 4. Okay. Let's see now what the question is. It says this is a star and this star's temperature is 500 Kelvin. The radius is R. So it's radiating how much? This much power. Then it says another star is there. So radius is R by 2. Temperature is 1000 Kelvin. How much power it is radiating? Okay. So simple, direct formula based question. This is 450. Since it's a star, you consider them as black body. Okay, this is also a black body. So black body means E value 1. So formula is A sigma T to the power 4. So A here is what? 4 pi R square. So sigma is sigma only. T to the power 4 means 500 to the power 4. Remember, temperature in Kelvin only. Don't write it in degree centigrade. Okay. So this is given to us. He is asking this. What is this now? P equal to A. That is 4 pi R by 2 whole square into sigma into 1000 to the power 4. Okay, so what this is now here? This is 4 pi R square by 4 into sigma into. Now here was 500 Kelvin. So this we can write as 500 into 2 to the power 4. Okay, so what we have? 4 pi R square into sigma into 500 to the power 4 into what? 2 to the power 4 by 4. Correct? Okay, so this value 4 pi R square into sigma into 500 to the power 4. Its value is given to you as 450. This entire value is given to us as 450. So this is 450 into what? This is 2 to the power 4, that is 4 into 4 by 4. So here it is coming as how much? 1800. So be 1800 watt. Okay, this is radiating with the greater R value but lesser temperature. Here temperature is doubled but radius is half. So how much power this is generating? 1800, whereas this was generating 450. Okay, let's see next. Okay, there is one star. Let's say first we'll do it without black body and then we'll talk it about black body. So let's say this is a star here and its heat generated is Q. So what is its temperature? Easy, simple. Same formula based question directly. Okay, so power is, formula says EA sigma T to the power 4. Non-black body. That's why E I have written. Okay. So if this is Q, this is E, this is 4 pi R square. Sigma is constant, T to the power 4. So T to the power 4 equal to this by this. So T to the power 4 equal to Q by E sigma 4 pi R square. E sigma 4 pi R square. So T equal to what? fourth power of this, E sigma 4 pi r square to the power 1 by 4. This is for non-black body. If black body is there, this E will not be there. E will disappear. So Q by sigma 4 pi r square to the power 1 by 4. Okay. Then, okay, temperature of black body is 727 degrees centigrade. Then power radiated is proportional to. Now see, they have given in degree centigrade. What we have to do? Convert in Kelvin. Okay, so what power is? Power is proportional to T to the power 4, we know that. Because he is talking in terms of temperature, so we are also talking in terms of temperature. No area, nothing we are writing. Okay, so P is proportional to what? 727 plus 273 to the power 4. That's all. So how much is this? 1000. P is proportional to 1000 to the power 4. Okay, that's all. Okay, Wien's law. Now what's Wien's law? Wien's law says that as the temperature of a body is increasing, as the temperature of body increases, then the wavelength that it is radiating decreases. Okay, as the temperature of body increasing. So what kind of radiations it is? These are electromagnetic waves, electromagnetic radiation. So if temperature of the body increases, then what happens? If the temperature of body increases, then power increases, or energy radiated increases. Energy radiated increases, right? And energy is inversely proportional to wavelength. We know that. When we are talking about radiations, then we should talk about waves also, wavelength also. So energy is inversely proportional to lambda. So Wien's law says that lambda into T is constant. Okay. So lambda corresponding to maximum power into T is constant. So at different temperature, obviously lambda will be different only. So lambda T equal to constant, and this constant is actually V. Okay, B, and B is called Wien's constant. Wien's constant. Okay, and it has got some value. That value I need to check whether it's 2.8 into 10 to the power minus 3 or something. Okay, I don't remember exactly at the moment. Okay, that's Wien's constant. It will be given to you in the problem. Don't worry. Okay, so lambda max into T. Lambda max into T is constant. This is our Wien's law. Direct questions are going to come on this also. At this temperature, this is lambda, then at that temperature, what will be lambda value? So you have to identify its Wien's laws question. Okay? Alright. Then what else is there? Then we have Newton's law. Newton's law of cooling. Okay, Newton's law of cooling. What is Newton's law of cooling? Now, Newton's law of cooling is applicable when the temperature difference between two objects is relatively smaller. Okay, for smaller temperature difference only it matters. That means here we are not talking about how much you are radiating the power. Radiation power, okay, is not dependent on temperature difference. But this here is cooling. How faster an object is cooling, that depends on temperature difference between object and surroundings. So when object and surrounding temperature is not very large, we use Newton's law of cooling. Or in the question itself, they will mention you based on Newton's law of cooling. So what it is here, what we do, we say rate of fall of temperature of the object, dt by dt, is directly proportional to is directly proportional to, okay, delta T minus T naught. Okay, delta T minus T naught. What is delta T? Let me write it, okay. I'm thinking that I should not derive it, okay, because derivation is unnecessarily, we have to remember only the final thing, okay. So fine, okay. If anything is there, we will add into that, okay. dt by dt equal to k delta T minus T naught. Okay, now what these are? What is dt? What is delta T? What is T naught? So T naught actually is surrounding temperature. Temperature of surrounding. Okay, surrounding temperature, and it is going to remain constant because of the body who is losing the heat. Surroundings temperature is not going to change. dt here represents what? dt means the temperature change of the body. Okay, that is T1 minus T2. Suppose T1 is initial temperature and T2 is final temperature. Okay, so this is dt represents what? Wait, I'll write first what it is. Temperature difference. Whose temperature difference? Of object itself, because its temperature is going down. So dt basically is T1 minus T2. Okay, temperature of objects. Temperatures of object. Okay, that's dt. Okay, this is time. So that means, shall I write here delta T by T? Yes, why not? And what is this delta T? Don't write this as delta T, that's what I was thinking. That is, right, T average. Okay, write this as T average. What is T average? T average means average temperature of object. Why like this? Because object's temperature is changing. So we write average temperature of object. That means this is what? This is T1 plus T2 by 2. Okay, that's it. So here is delta T by T equal to K T1 plus T2 by 2 minus T naught. Now this formula we have to remember, and this is what we are going to use in Newton's law of cooling. Okay, so how will be the question asked? Let's see if it is there. Any question? No, we'll make it. Okay, so on Newton's law of cooling, one question we are going to make. Let's assume that there is one object here. Its temperature, let's assume, is 80 degrees centigrade. Initial temperature. Okay, and it says that outside temperature is, let's assume, 40 degrees centigrade. This surrounding. Okay, so question asks, initial temperature is 80, then final temperature of this object becomes 60 in 10 minutes. In 10 minutes. Then question asks, find in how much time temperature of object will become 50 degrees centigrade. That's how the question will be asked from you. Okay. So initially what is given? 80 to 60 in 10 minutes. So we'll write what is that. Okay. So first step is, what is the formula? Formula says delta T by T. Delta T is what? Temperature difference of object. T1 minus T2. T1 minus T2 is 80 minus 60. And how many minutes? Say 10 minutes. Okay. Equal to what? K. K is constant. Average temperature 80 plus 60 by 2. 80 plus 60 by 2 minus 40. Let it be here like this. Now what he asked? When temperature of object will become 50. So now 80 to 60 in 10 minutes. Then 60 to 50 in how much time? Okay. So second step, same formula, 60 minus 50 by T. This T only we are finding, equal to K, average temperature, 60 plus 50 by 2. This is same 40. What? Divided. K is cancelled. Okay, now what this is? This is 20 by 10. Okay, so let it be 20 by 10. Here is what? 10 by T. Here is what? 80 plus 60, 140, 140 by 2, 70, 70 minus 40 is 30. By 60 plus 50 is 110, 110 by 2 is 55. 55 minus 40, that is 15. Okay, so this is 2. So 20 by 10 equal to 10 by T into 2. Okay, so this is 20 and this is also 20. So T equal to 10 seconds. So further 10 seconds, its temperature is going to decrease by 10 degrees centigrade. First 10 minutes it decreased by 20, now it's going to decrease by 10. This kinds of questions are there. One more you can solve if you want, same way. Okay, one more we can solve. We have a little bit of time left. Okay, so here it is. This is the body. Okay, it's initial temperature 40 degrees centigrade. Okay, and final temperature 10 degrees centigrade, atmospheric temperature 5 degrees centigrade. Okay, so question says you, if temperature of object decreases from 40 degrees centigrade to 10 degrees centigrade in 30 minutes, find in how much time temperature decreased from 30 degrees centigrade to 20 degrees centigrade. Okay, and this is here. Let's do that. This is given. Okay, so first step 40 to 10. So 40 minus 10 by how much time? 30 minutes equal to K, average value 40 plus 10 by 2, that is 25, minus outside temperature 5. Okay, second step 30 to 20. So 30 minus 20 by T equal to K. Okay, 30 plus 20 by 2, that is again 25, minus 5. Now we can see that this and this are exactly equal. So this and this cancel, K and K cancel. Okay, then what we have? 40 minus 10 by 30. That means 30 by 30. 30 by 30 equal to 10 by T equal to 1. Okay, so 30 by 30 means 1 equal to 10 by T. So T equal to 10 minutes. T equal to 10 minutes. Okay, so like this, there will be questions on Newton's law of cooling. They can ask you time, or they can ask you at times what is the atmospheric temperature. They will give you time over here. They will ask surroundings temperature. So it depends. Okay, so that's all. This is what heat transfer is. Like this, we have completed heat and thermodynamics. Okay. Tomorrow's class, I'll be starting simple harmonic motion. Simple harmonic motion, then waves. Then 11th portion is over. Okay, students. So scan your QR code. It's taking time today, too much. Yes, it is here. So scan it. Okay, students, then see you tomorrow. Bye bye.